studied informatics in Copenhagen. He was very successful in this context. He was later on, when he got his PhD there, he was a visiting researcher at Stanford University and with Microsoft. And since 2006, he is a professor of software engineering in the University of Dortmund, which is in Germany. Some of you may know that.
This is beginning on a great note. That's good. Continue.
He's not only just a professor there, he's the post for now he is leading an institute which is called the Lamar Institute. I have no idea what this means.
It's actually named after Hedy Lamar, who is not only an actor but also a rather interesting engineer.
Okay, for machine learning and artificial intelligence, for a while he was director of the Fraunhofer Institute of Software Engineering, which was distributed in Berlin and in Dortmund. And in Berlin, we sometimes went to the restaurant.
That's right.
And he told me about how much he was suffering from this job. It was very interesting. He is an editor of in the editorial blog of communications of the ACM. It's very honorable and very interesting. And last year he got an award, a very special award of CAF, which is computer-aided verification. And as I understood, he got this award not for very recent research, but for research 20 years ago, which later on turned out to be so fundamental and influential that he got the award later. That is interesting. He got an award for the beats 20 years ago. So maybe some of you will still get this kind of. Okay, so
it's not doesn't
this one I want to say.
Okay, but that's enough for time. Thank you very much. Thanks so much for inviting me, and thank you for accommodating my crazy schedule. Of course, I'm always terrified of making a mistake to get bad notes in Wolfgang's black book here.
Yeah.
And so I was very careful when I chose the title. I mean, last year I gave a talk here with this title up here, written in small. And this is now my update for this year. I didn't want to give the same talk, of course. But then I had the following problem. I knew he'd written this title in the program. And so if I changed the title, he would immediately complain, which he did. He said, "What is the title?" And I had to tell him, well, it's actually up there. Okay. So what I will do is I will just try to set the context of what I'm doing. And this will be a very brief, I hope, repetition of what I was talking about last year. And then I want to give you an update of what happened since, and that will be the main focus of the talk. So I work on something called combinatorial logic synthesis, which is a framework for doing type-based component-oriented program synthesis. And here's how it works. You have a component repository which is exposed to synthesis simply in the form of a set of typed function symbols. And what synthesis does is it can automatically compose those functions according to the types that sit on the interfaces of these functions and according to a goal type. So it's really sort of like doing Lego automatically, where types define the interfaces of the building blocks. And so what comes out of that is possibly a set of combinatorial programs, which are really function applications and function compositions, according to the type specifications and some underlying type system. We don't just generate one program. Quite possibly there might be many programs satisfying the goal specification. For example, you might have several functions in the repository having equivalent types. They may not have to be the same, but they could be equivalent, for example, in some sort of subtyping relation that comes with the type system. Now, in a normal type system, like the one suggested here by my black types, you wouldn't be able to specify precisely enough what it is that you want, and you would not be able to specify precisely enough the semantics of your components or functions. So for that reason, we chose to work from the outset based on a very interesting type system. As a type theorist, it's something that excited me a lot, but I'll spare you the details of that. This type system was discovered in 1980 and has been studied very intensely in the lambda calculus community since then. It's an incredibly expressive type system, and it has the charm that the type rules are very simple. They're deceptively simple, but it's possible to explain to a good bachelor student how to work with this system. And this remains actually sort of my litmus test for what I do. I don't want to put anything into the system that I cannot, at least at some level of operationalization, explain to a good bachelor student. What we do with these intersections is we use them to, for example, specify semantic properties of the interface, on the interfaces that you would not be able to specify in a normal, as I call it, native type system. The native type system is the type system of the programming language in which the implementation of your components is written. It could be Python, it could be Java, it could in fact be anything. The way we expose the components in the repository would then be by wrapping them into some kind of functional formalism. For that we have used various languages. That's not so important. The current version that I'm talking about here is written in Python, and you can also specify your components in Python, but you don't have to do that. So for example, here I'm making a little toy example where I'm kind of suggesting generating various forms of neural network implementations. So for example, F here might be one layer, H might be an activation function, and N is then a net that arises by composing in a certain way these two. Yes?
Real should be multidimensional, right?
Yeah. I mean, this is just all toy. So think real to some, raised to some dimension. But the point here is that these intersections are used to specify semantic intent. And so essentially this intersection type system gives you a multi-dimensional type system where one object can have many types. And so what comes out of it is in general not programs, but it might be meta-programs, functional compositions of meta-functions, which when executed actually generate the code in possibly some other language that you're interested in. So what comes out of it is not necessarily, as I said, one program, but it might be a whole family of programs, and this is something that's interesting to me in the applications. So one setting in software engineering terms for which this framework, I think, is very directly amenable is the automatic generation of product families, programs, where each program differs from the others in some respect, but maybe shares some general overall structure. Okay, so we have put this to use in a number of industrial contexts, and we have also put it in touch with machine learning. For example, here is an example of something I showed last year, how we were able to close a generating test loop using this framework. So we generate families of, in this case, it was families of sample-based motion plans for controlling robots. And this process was controlled by a learning module which controlled the configuration of various components in the repository. Think of it as generating some configuration vector of numbers, which would then be used to control the configuration of certain components in the repository. And by closing this generative loop together with that learning component, we were able to automate the computation of Pareto funds according to some KPIs that were interesting for this application. And so this was an interesting one example I showed last year. There are several ways you can think of extending this framework. You can operate here at the component repository. You can generate components. The whole solution set to a query could be summarized as a tree grammar, because every generated program at this level here is a tree, syntactically speaking. And that's nice because you can then summarize also infinite solution sets in the form of a tree grammar, and you can then start making various kinds of, for example, algebraic transformations on that grammar, where you can study various enumeration strategies of interest. And then at the far end here, you can put tests or filters or measurements, and this was all at work in the slide I showed before. And so last year I had a chance to show you some cool animations coming from the motion planning area. Since then we did a number of further industrial application studies with this framework, including also intra-logistical designs, which we have integrated with a simulation framework, in this case a framework called AnyLogic, so that we can generate variations of intra-logistical designs, and then we can automatically simulate them, and then we can automatically measure on them, and then we can choose the best ones, and we can perform a kind of automated design optimization in this way. We have also put CLS together with CAD tooling, and I showed you last year how we could use this to automatically generate families of CAD designs. And I think this is just a very nice video, so I'll show you that again. What you see here is sort of a taxonomy of parts that go into the design, in this case of robotic arms. And coming back to my previous slide, these various part specifications here can be rather naturally injected into this intersection type-based type system. You can build up taxonomies of parts, which then become amenable to the synthesis tool, so that it correctly composes these various parts to realize some global design, which you can then measure on. In this case, of course, you can also start playing with it in the CAD tool. So that's sort of what I was showing you last year. And now I want to move to the sort of the main technical part of this talk, which is about essentially powering up the type system so that we can achieve more powerful specifications and more powerful scenarios of synthesis. So actually the slides here are not coming out as well as I thought. It's a little kind of not so sharp. I don't know what to do about it, but I hope you can see it. So what we now wanted to do was to see if we could leave this basis of just having these intersection type specifications, which are still there, and they're still very useful, but we discovered from case studies a number of cases where it would be nice to be able to inject more information into specifications. In particular, once you get into touch with, in a serious way, with optimization problems or learning problems, things like being able to perform automatic configuration of various numerical spaces already at the level of the synthesis becomes important. And so the main result that I will sketch for you today here is how we did this in such a way that I think we stay in tune with my litmus test. We're not leaving the level of sort of simplicity, at least at some level of exposition, where you can have students work with this without understanding a whole lot of type theory, but at the same time, we remain deeply rooted in type theory itself. And this is important to me for a number of reasons, which I'll touch on in a little bit. So we still have these intersection types, we have function types, we have type constructors, and now we have something called literals. And these literals can be used in type specifications in interfaces. For example, here you might imagine these numbers here referring to coordinates. And so, for example, this function type here might say you take something with x coordinate 3 and you move it by applying this function to something that now has x coordinate 4, for example. And that might mean, say, moving right on a grid. I'll use this grid scenario. It's just a toy scenario, just to have some access to some easily understandable examples. These literals can actually, in our Python implementation, be any Python object that you care to mention, any Python expression, but it remains uninterpreted at the level of specifications. These intersection types, as I said, are very powerful. You can express any finite function table using these types. Now here is the extension. The extension, and I realize that I may be the only person in the room who has like a deep interest in type theory, but I will mention a couple of things. So these two new forms here are really special forms of universal quantifiers. In type theory, they would be dependent products in margin-left type theory. Why am I mentioning that? It's important to me, but why is it important to me? It's important to me because that type theory, dependent type theory, as it's called, or margin-left type theory, has had a spectacular set of successes over the last years. You may not know that unless you follow the field, but it's not just machine learning that has witnessed spectacular progress over the last years. There is a lot of work going on in formal mathematics that has been spectacularly successful. In fact, two field specialists have been working over some years in using this kind of type theory to formalize real mathematical proofs and having them machine checked. And this is something that people would laugh at maybe if you were told them about this 25 years ago, but that is no longer the case. So Vladimir Voevodsky was driving before he died too soon a few years ago something called homotopy type theory, which gave an enormous push to the field. And Terence Tao, who's been working in a different area of mathematics, more like number theory and combinatorics, has been using a proof-checking system called Lean, created by Leonardo de Mora, who's now working at Amazon Web Services and driving verification work there in a spectacular way. So this is the whole background. I just wanted to mention to you why it's important to me that we stay within this sort of framework, because that way we sit tightly inside a much larger development, which is significant. Okay, so what can we do? We can quantify over literals, and we can now quantify also over term variables. These term variables refer to parts of the trees, or to the trees that are being generated. So this quantifier says that for all x, that means for all parts of the tree, for all trees that we're generating having a certain type, a certain property phi should hold. P here ranges over arbitrary computable predicates that we can enter into the specifications. And that actually leads to synthesis problem becoming undecidable if you don't in any way limit this set of predicates. But we are able to also identify a decidable fragment of this system based on a restriction of those predicates. But you're not confined to that restriction, in which case you still get useful functionality out of the framework, which I hope I'll be able to explain briefly in a bit. So for example here, you can see now the type of a component which would mean that applying this function with this type would mean moving right on a grid, for example. It says for all alpha, alpha ranging over pairs of natural numbers, so they would be interpretable as positions on the grid, beta as well. And here the predicate now saying that beta is equal to the first projection of alpha plus 1 and the second projection of alpha in the second component. So that would mean moving right on a grid and taking a position with value alpha to a position of value beta, the following position. Yes?
What is the blue arrow in this?
The blue arrow here, that's a function type, and this is an implication. So the blue arrow is this one. That's ranged over by sigma. That's sort of one of those basic intersection types of normal function types. And what we now add is this implicational form with these restricted forms of dependent product universal quantifications. And so, for example, you can express interesting things about the form of the generated trees. For example, here we require that if x is apart, then the number of motors in x, that's a predicate on the generated trees. You now must imagine that during synthesis, a tree arises, and this predicate now decides on the fly whether the generated tree has the properties that the predicate specifies. And so that's a very powerful thing. And so the terms, that is, the trees that we generate now, are not just normal combinatory expressions where you have like an expression applied to another expression. We can now also refer to these literals inside the combinatory terms. So for example, we might have a combinator down that takes two pairs of literals and performs what would be a down movement. So to just set the stage now for the formal modeling of what synthesis does, we now have a type environment consisting of typed combinators, A1 through AN are, you can think of them as function symbols, and phi 1 to phi n are corresponding interfaces now using this enhanced type system, type theory. We then introduce also a special literal environment which gives identifiers to the various literals that can appear inside the specification so that they become accessible to the synthesis machinery. Here's now the type system. This part of the type system, which is up here, is the version I had last year, and we now control these new features with the quantifiers and the literals using these three rules. I don't have the time here to go into the details of that, and I'm sure I would probably start boring you if I did it, but I brought it along in order to show that this logic indeed is a standard fragment of dependent type theory. What we have here are the usual forms of quantifier eliminations by instantiating a dependent product but now split into two different families, one for literals and one for tree variables. And so you can now start playing with this, and you can see that, for example, on a maze like this, we can have a combinator that moves to the right, and we can have a literal repository that kind of sets the stage of the maze. It would in this case define which coordinates in the maze are relevant and are accessible to synthesis. There's some theory going on here. This lemma here is important because it shows that the nature of the intersection type operator remains retained in this extension. And you can see this rule is, the derivability of this rule is what this shows, is that the standard rule for the intersection type introduction is retained. What does that say? It says essentially that this operator here is a kind of strong conjunction. It's not a normal Boolean conjunction. If you had a normal Boolean conjunction, you would say that the proof of a conjunction would be one proof of one conjunct and possibly a quite different proof of the other conjunct. The intersection type operator here is special. It's a strong conjunction because it requires that the proof of the two conjuncts be the same. That is what gives you this very special nature of this type system, where I said that it's a multi-dimensional type system where one and the same object can have many types, any finite number of types. Type checking in this system is actually decidable. Here we use the decidability of the predicates, but inhabitation is not decidable, it's only semi-decidable. Inhabitation means, given an environment, that means given a repository, can you find a program with a given goal type? So the so-called inhabitation problem is the logical foundation for synthesis here. And because the type theory we're in corresponds one-to-one, is isomorphic to a mathematical logic, this problem is also the provability problem in some higher type system. This decidable fragment comes about when we restrict what those predicates can be. In particular, it's interesting from an application perspective to be able to express equalities and disequalities. And so, therefore, we were interested in the fragment where this is possible. And it actually turns out to be a very interesting and useful fragment. And so that now becomes the main restriction on the predicate language which we need to achieve decidability. Again, from a technical perspective, it's really interesting that the decidability of this problem is established by reduction to a very recent result, actually, in this field, 2010. I mean, this is a very classical field of mathematical logic. And of course, you know, this sort of stuff has been studied for many, many, many years in theoretical computer science. And this fragment actually corresponds to something that was studied by Royce and Seidel in 2010. And so we're able to show the decidability of the basic decision problem underlying the synthesis framework that we're looking at here. And so what you see here are now some slides that talk about our study. We have a paper that's also cited here this year, where my PhD, my postdoc, Andrew Dudenhofen, who did these slides for me, he played the game of asking ChatGPT about FCRP, which is the technical name for this new system. It wasn't very old when he started asking these things. So, for example, ChatGPT says FCOP isn't just an update for CLS, it's faster, sweeter, snazzier, a whole new level. You ask me how it got those ideas, I can't tell you. Okay. So before we had this workflow last year where we would produce tree grammars, and here's now the second thing I want to get across, which I'm a bit proud of actually here. The first thing I was proud of was being able to power up this framework in such a way that it conservatively extends the previous framework and it sits in an identifiable fragment of Martin-Löf type theory. That was the first brownie point I wanted to give myself. The second one is that in making this extension, we showed that we move from a tree grammar representation of the solution set into a logic program representation. So, whereas before we could use tree grammar formalisms to represent possibly infinite solution sets with these predicates, what we now use and is in a total correspondence theoretically to the synthesis problem is a set of Horn clauses. And so now enumerating the solutions becomes an exercise in enumerating enumerating from the Herbert model of that restricted logic program. And so that means the theoretical foundations of the extension is as good as I could have hoped for. And so now I'm running short of time, and I already made the main points I want to bring across in this talk. So let me just illustrate the use of logic program formalism to represent what comes out of the generation. So it's a whole family of programs. That family of programs can be represented now as being recognized by a set of Horn clauses, which is generated by the synthesizer. And you can see maybe here from harking back to the previous example that types with possibly parameters now become Horn clause predicate names. They may take arguments. Those arguments may consist of applications of combinators. Those are the terms. So now you see the application here of a predicate to a term. This is what allows us to implement this idea of quantifying over the terms that are being generated to filter out terms or to select terms that satisfy certain predicates while we're generating them. I think that's an extremely satisfying correspondence. FCL stands trembling as FCLP rockets in a supersonic revolution, rewriting the rules. Okay, so that was another. The following slides simply show various dimensions along which the enhanced specification possibilities with this predicate and quantifier framework is able to achieve enormous succinctness in specifications which would previously have blown up. And it also raises the possibility of playing with the way you design a repository. For example, in some scenarios, you might experience a blow-up in a number of different literal combinations that would have to be seen during synthesis. But you can perform a kind of systematic engineering of the way you specify your repository, and you can kind of hide things behind types and combinators so that you don't have to expose this explosion to synthesis itself. It might, however, then mean that you would have to provide some further functionality to explore that space of literals. as part of the program that you generate. So you don't necessarily have to generate, you don't have to perform all the logic at generation time that you can think of. You can generate programs which then, when the generated program runs, performs configurations on the parameter space of interest. And this is also illustrated here, where you now start actually pushing configuration code into the interpretation of combinators, which then becomes active once you execute the specified programs. So that creates a very, very flexible framework where now you can think of this Horn logic-based representation of a solution set as something onto which you could graft a lot of further programmatic instruments to do optimization, constraint solving, and other things of interest. SCLP empowers the CLS framework to operate at unprecedented levels of efficiency, scalability, and precision that came out of Dortmund. And so here is a couple more slides showing how we are able to push things into the specifications which we would previously have to laboriously work after the fact to establish, to filter out, for example, certain subsets of solutions satisfying properties of interest. Imagine a maze FCL bundles around like a lost copy while FCLP zooms through like a laser beam. I think that's a nice caption for the end. So let me just go back real quick to my presentation here to end my talk with a slide where I just mentioned what we intend to do next. And so what we intend to do now is to pursue this idea I already touched upon, grafting onto this logic program representation with constraint solvers, optimizers, and also machine learning techniques. There is a field which interests me enormously, which I think we can now attack in a very serious way, which I would call simulation-based machine learning. And here, maybe if I have, do I have still 2 minutes?
Yeah.
Not more than 2 minutes. I'm going to just mention something which I think is enormously interesting, coming out of the physics group in Dortmund. Some of the physicists in Dortmund are also part of the Machine Learning Institute. And they recently had a spectacular development in this area here. What they did was, in the context of a project called the Ice Cube Project, which is a project in astrophysics, where on the South Pole you have these kilometer-long ice rafts, and putting detectors on these things, they can detect things like neutrinos coming from outer space. And so the problem they had was that interpreting the empirical data that gets into the detectors is just totally impossible. You can't, humans cannot detect any meaningful signals of interest for neutrinos because they are very weak and so on. So what did they do? Well, they created, based on physical theory, they created a simulation model. They used that simulation model, and this simulation model essentially implements some funky intervals from theoretical physics. They ran this simulator on a neural net, training the net to detect patterns that the simulation model would teach it to look for. And they then used that model, that trained model, on the empirical material that they got out of the sensors at the South Pole. Now, you're talking petabytes of data there, okay? But by doing that, they were actually able to find structures in that empirical material that allowed them to interpret that material, leading to entirely new insights into the nature of cosmic neutrino radiation coming from the Milky Way. That resulted in a fairly big deal that was published in Science. One of the really basic innovations in that project was the use of simulation-based machine learning techniques. So this is the sort of stuff that I would like to be able to further help with this framework, where the idea would be that we could help generate whole families of simulation models of interest. There's also the idea of doing the categorical framework for synthesizing learners. There's some interest in the logic community in understanding what is actually a learning mechanism and how can we describe various families of learning mechanisms. What I see this framework being able to do here is to help automate the exploration of various forms of learning architectures. And with that, I think Wolfgang now wants to end my talk. Thank you for your attention.
There may be one urgent question, but this seems not to be the case. Okay, so we reconvene at 3 o'clock, but we should have been up now.
Nee, ich habe da kam noch angeguckt. Ich wollte nur sozusagen den Ziel aufhören, I will